All right, guys, welcome back to our final example in this section. And we're going to number 14 in our homework set. So let's see what number 14 has in store for us. Okay, so a stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 60 centimeters per second. Find the rate at which the area within the circle is increasing after 1 second, 3 seconds, 5 seconds. What can you conclude? All right. So let's draw a picture. So someone dropped a stone in a pond and it creates ripples, right? And have you thrown a stone in the water and watched the ripples move outward? They start off small from the stone, right? And then they get bigger and bigger and bigger. Okay? So that's the situation we have. And the information we're given is it's just one ripple, right? So it looks like I made a whole bunch of different ripples, but really this is the same ripple. Okay, it starts off here, and then this little ripple slowly but surely and steadily gets bigger and bigger. And I say steadily because they tell us that the ripple is traveling outward at a speed of 60 centimeters per second. Okay, so let's revisit this problem. We want to find the rate at which the area within the circle is increasing. Okay, so what is area? It's pi r squared. Area is pi r squared. Okay, so let me just write that as a little reminder. Area is pi r squared. So our area is dependent on what? On the radius. And the radius is changing. And the radius is changing at what rate? 60 centimeters per second. So let's kind of examine that. Okay, so at the radius is changing, so I'm assuming it's going to be a function of t. After 1 second, what's your radius? Let's see, 1 second passes, so 60 centimeters. 2 seconds pass. What's the radius of this ripple now? Well, 60 centimeters per second, so 2 seconds is going to be 120. All right, 60 times 2. And then what's R of 3? Well, 60 centimeters per second times 3 seconds is 180 centimeters. Okay, so let's try to generalize this. What's R of t? Well, what are we doing to get all of these numbers? We're taking the 60 centimeters per second and we're multiplying it by the time. So that's R of t. And so the area is going to depend on where the radius is. So the area is a function of the radius, and the radius is a function of t. So our area function is really a function of time, because as time increases, we can clearly see that the circles are getting bigger, so the area is going to increase. So it's going to be pi r of t squared. Okay, and what is r of t? R of t is 60. So it's really going to be pi of 60t all squared. All right, well, let's clean that up. What's 60 squared? 36 with 2 zeros. Then we have our pi. Then we have t squared. So this is our area function. We had to actually figure out the area function this time. So that was a great accomplishment. And we did that really, it was a very visual problem. And we kind of had to start from scratch. I think a big part of figuring out the area function is realizing that area is dependent on the radius. So we actually focused on the radius first. Then we were able to find the area function. All right, and now what's the question? Now that we have the area, we want to find the rate that the area is increasing or the area is changing. Well, what do we think when we think rate that something's increasing, rate that something's changing? We're thinking of derivative. So we have to find the derivative of our area function. All right, so the rate of increasing, the rate of changing, we have to look at the derivative, okay? Just our power function, because remember pi is a constant, bring down that to 3600 times 2, pi times t. All right, and now we want to know the rate it's changing at 1 second, at 3 seconds, at 5 seconds. Okay, so this is the easy part. This was the hard part. This is the hard stuff. But now we're just finally able to plug in and use our function. So I'm just going to write it all out and then we'll do all the calculations at the end. So we're plugging in 1, 3, and 5 into our derivative function. Okay. All right, so what's our calculator spit out? We'll go to just the nearest ones place. Okay. So at 1, the area is increasing at a rate of 22,619. What are the units? Remember, we can always go back, rate of change for the area, dA dt. Area would be in terms of areas square units. And time is in terms of seconds. So our units are centimeters square per second. All right, and then at 3 seconds, 67,858 centimeters squared per second. And then at 5 seconds, 1,013.97 centimeters squared per second. All right, and then they want to know, like, what do we notice? Well, even though the radius is changing at a constant rate, right? We're just going 60 miles, 60 centimeters per second, right? So we're not increasing that speed, the velocity is constant. But what's happening with the area? We're getting bigger and bigger and bigger, right? The area on this circle is increasing, the rate that it's increasing, that rate is increasing. So even though the radius is increasing at the same rate, the area is getting bigger and bigger and bigger and bigger, almost exponentially, right? So even though the rate and the radius is changing the same amount each time interval, the rate that we're going from this area to the next area, that rate is much smaller compared to larger radiuses, right? Compared to going from this area to the next circle out. That rate's much bigger because the rate that it's increasing is increasing itself.